All right. You are going to define Le Chatelier's principle. Juan, when? I wrote Juan. Not yet. Before the system is stressed, it is at equilibrium. Is stressed. Oh, I like that. The system shifts. Stress. The stress. So think of it like a little story. What's happening at first? Oh, my system is at equilibrium. It's just hanging out, cozy, chilling. Ah, it's stressed. So what's it gonna do with stress? Oh my God, it shifts. And why is it shifting? It's shifting in order to minimize the stress. Okay. This is how I get through a Friday afternoon. All right. It's a weird place in my house. My son is exactly like me. So it's a weird place in the Spence Northcott household. In the reaction above, in the forward reaction, is that forward reaction absorbing heat or is it releasing heat? It is releasing heat because our heat term is over here. So it is the forward reaction releases heat. What does the reverse reaction do? It absorbs heat. So if we decrease the temperature, basically think about it this way. You're putting your system maybe into an ice bath. Yes? Where is the heat going? What direction is the heat traveling? Is it traveling from the surroundings to the system, or is it traveling from the system to the surroundings? From the system to the surroundings, because the system is hotter and the ice bath is cold. So what's going to happen is the heat's going to move out into the ice bath. The ice is going to start to melt, yes? And the system is going to decrease in temperature. Okay, so if we decrease the temperature, the amount of heat in the system has decreased. According to Le Chatelier, the system would like to bring the temperature back. Hang on, we decreased the temperature. It wants to bring the temperature back up. Sorry, I wrote D, but I meant up. Because we decreased it, the system wants to bring it up, because minimizing it means going in the opposite direction. So the system is going to shift in the direction that, is it going to shift in the direction that releases heat or that absorbs heat to bring the temperature back up? Oh, I know this one messes with you because you think, oh, if I absorb heat, I get hotter. But that's not the case. What absorbing heat means, when you absorb heat, you get colder. I know, that makes, it's very unhappy, right? When we absorb heat, what we're doing is we're taking heat, kinetic energy, and we're converting it into potential energy. What does that mean about the quantity of kinetic energy? There's less kinetic energy. Hang on. There's less kinetic energy. And what quantity measures kinetic energy? What measuring device can I use to measure kinetic energy? Temperature measures kinetic energy. It's hard to phrase that question. It was really hard to make it like clear. Temperature measures kinetic energy. So if we have less kinetic energy, the temperature is, hang on, temperature measures kinetic energy. So if we have less kinetic energy, the temperature is lower. So let's go through that again. If we absorb heat, what that really means is we're taking kinetic energy, which is associated with a higher temperature, and we're converting it into potential energy, which is associated with a lower temperature. Yes? So if you absorb heat, you get colder. And if that makes you unhappy, think about it in the reverse direction. What is the most famous exothermic reaction? It is fire. Yes? Fire is our most famous exothermic reaction. Now, if we have ice cubes melting is endothermic. Yeah. Making ice cubes is exothermic. And you know, well, think about it. Have you ever felt the back of a freezer or a fridge? It's really hot because you're taking the heat out of the water and pumping it out the back of the fridge or the freezer. We're not going to talk about that right now because it's Fast Friday and we don't have time. Okie doke, yeah. So fire is exothermic. And does fire release heat or does fire absorb heat? Fire releases heat. And what happens to the temperature when we have a fire? Temperature what? Well, if I have a fire, what's the temperature like compared to no fire? It's hotter, yes? So the temperature increases when I have a fire as opposed to no fire, yes? It sounded crazy because I'm like, fire, the temperature gets lower. And I'm like, oh, ah! Okay, temperature gets higher. So basically, if you have something that is exothermic, you are releasing heat and the temperature gets higher. So if what we have done to the system is to lower the temperature, the system is going to shift in the exothermic direction to release heat to bring the temperature up again. If we increase temperature, the system is going to shift to absorb heat, which turns it into potential energy, which actually means that our temperature gets lower. Whew. I know it seems counterintuitive. You absorb heat, you get colder. It's true. I know. It's because heat means something a little different in chemistry than it does in like normal life. Okay. So yeah, we shift to the right because we're shifting towards the heat term. So if we decrease the temperature, which reaction is favored, the endo or the exothermic? If by decrease temperature, nature wants to increase temperature by releasing heat, so exothermic. Since it releases heat to bring the temperature back up. If we increase the temperature, that favors the endothermic reaction since it absorbs heat to bring the temperature back down. You can think of an endothermic reaction like a sponge, yes? And the water on your desk would be like the heat. What do you do to get rid of the extra water? You absorb it with the sponge, the endothermic. Anyway, it's a little bit of a weird analogy, but there we go. So let's take a look at this reaction here. We have N2 plus 3H2 in equilibrium with 2 NH3, and our kilojoules are over on the right-hand side. And if we're going to look at our rate diagram, what do rate diagrams do at the very beginning? Only if you are starting with only reactants, okay? However, because we are looking at a stress, that means that the system must already be at equilibrium because, oh, is that on the other one? No, no. Oh, where did we define? Oh, here. Look, when a system is at equilibrium. Yes, so we are at equilibrium. And if we are at equilibrium, what are the two rates like? They are equal. So there's our forward, and there's our reverse. And we have just decreased the temperature, am I correct? Yes, we decreased the temperature. Oops. And I'm going to give you a choice of what your lines do. Okay, at this point. So right in that moment, when we decrease the temperature, what do our rates do? We like F? Yes. Okay, F is a good choice? Yes. Well, you know what? In my other class, it took a lot longer. We learned the sign languages for A through H, and I don't know. Anywho, you guys are just brilliant. That's all. What can I say? Block 4. We've gotten rid of all the deadwood now. Everyone else who wanted to drop has already dropped. You guys are the strong, the proud, the few, right? Okay. All right. So what does our forward rate do? Does it go up or down? Why does the forward rate increase? It what? Wait. We just decreased the temperature. We're not shifting yet. I want the rate. But yeah. What happens to the forward rate when we decrease temperature? It decreases because the particles are moving slower, so there's fewer collisions and there's less effective collisions. Okay, boom, down. Forward rate goes down. Reverse rate, oh, and I need my equation in front of me. It also goes down. Does it go down the same amount? Does it go down less? Or does it go down more? Changes in temperature. That's only for pressure. Changes in temperature affect the endothermic reaction rate more. So if we were to start with our forward rate and our reverse rate and they both get decreased, who gets decreased more? Yeah, so our forward rate decreases, our reverse rate decreases more because it is endothermic. So if I were to then draw my arrows, which arrow would be bigger and which arrow would be smaller? Why would reverse be bigger? If something decreases more, has it gotten bigger? If something decreases more, has it gotten smaller? So it didn't just get smaller, it got smaller. Yes? Reverse rate got smaller. Forward rate got smaller, but only smaller, not smaller. Yeah? So we now have this situation here where our forward rate is faster than our reverse rate. So our forward rate has decreased, but our reverse rate decreases more. And this video is going to be posted, so if you need to go back and go through this and listen to me say more, and smaller, again, you can do that. All right, and what happens now? Now we shift to minimize the stress, and what does that look like? A curve. And where do they meet? In the middle. Yeah, we get a G and an H, yes? And I'm just going to draw a little dot there to show that I know where I'm starting my shift. Concentration. Whew. We got 3 substances, therefore we need 1, 2, 3 lines. And we are decreasing temperature, so I want my NH3 here. And I'll have my N2 and my H2. Okay. And here we decrease the temperature, and this is our concentration, and that is our time. What happens to our concentrations? Which way is this thing shifting? We increase the temperature, so it's going to shift to absorb heat, which is which direction? Left, so it's shifting left. And if we are shifting left, what are we making? We're making N2 and H2. What are we using up? NH3, so NH3 is going to go down and N2 and H2 are going to go up. So Here goes my N2, it goes up. Now don't draw just yet. H2 also goes up, and NH3 goes down. Are we happy with my diagram? Why not? Yeah, we got coefficients that I did not look at, yes? And this one, although there's no coefficient there, that's of course a 1, yes? So if my n is changing, if it's going up by x from where it was, then H2 needs to go up by 3x. And NH3 needs to go down by 2x. Oh, that looks like 3x. Okay, I'll try that again. That looks a little bit better. I'm going to label it so it doesn't matter how bad my drawing is. There we are. Okay. Is good? Is good. All right. Can I scroll? Or are we still writing? I can scroll? Okay. Explain the following shift in terms of Le Chatelier's principle and in terms of rate. Our stress is that we have decreased the temperature. Therefore, the system wants to shift to bring the temperature back up. Yes, so it's going to shift to the right in order to do what with heat? Release heat to bring the temperature back up. In terms of rates, what does a decrease in temperature do to both the forward and reverse rates? It decreases both of them. A change in temperature affects which kind of thermic reaction more? Endo. And in this particular case, endothermic is which direction? Reverse. Okay, so in this case, this is the reverse reaction more. Therefore, the reverse was decreased more. So which reaction is faster than the other reaction? The forward is faster than the reverse. And the reason that makes sense is you can do your thing where you're like, okay, so my forward got smaller, my reverse got smaller, yes, and so my backwards reaction arrow is really small, my forwards arrow is really big, so my forward is greater than my reverse. So what are we making faster? Are we making reactants faster or are we making products? We're making products faster because our big arrow is going towards products, yes? There's our big arrow. We are making products faster. So we are making products faster than we are making... Red pen. Faster than we are making reactants, which means the equilibrium is shifting to the right. Okay. Whoa, what happened there? Come on. There we go. Okay, our next reaction here is our heat term here. Let's just take a look at that. And our temperature is increased. If it is increased, which direction is this equilibrium going to shift? We want to bring the temperature back down. Yes? Are we going to do that by releasing heat, or are we going to do that by absorbing heat? Absorbing heat. And which direction is the absorbing of heat? Left? Right, right, right? Huh? The reverse reaction absorbs heat? Does it? I know it's Friday and I know my brain is hurting. In order to absorb heat, it needs to be it needs to be a reactant. It needs to go in. When heat is absorbed, it enters the equation. When heat is absorbed, it enters the equation, yes? It's like the water enters the sponge. It's absorbed by the sponge. And if it enters the equation, that's the forward direction, yes? It's okay, it's Friday afternoon. I was going for a minute myself. I'm like, am I wrong? Oh, I've been doing chemistry since 1985. Same course. This is it. Do you know what? This is the one course in high school that hasn't actually changed the curriculum since 1985. Chemistry 12 is no different than when I took it. You might even get a question from my old provincial exam. I don't know. It was so long ago, I don't remember it. I don't remember what was easy and what was hard anymore. I more go off of what my students find easy and hard. Yeah, I don't know. I think COVID has messed people up a lot in terms of like, you know, being able to handle a certain amount of things. Like, I think normally over the course of grade 10, 11, 12, you gradually build up. It's like, okay, you do more in grade 10, then you do more in grade 11, and then by grade 12, you're like doing the most, and you sort of worked your way up to it. Whereas we were like, okay, grade 10, oh, you could do nothing for the last part of the year, or at least, you know, a lot of people did nothing. Well, my grade 12s did, because they had to get into university. And they knew they were going to be like, I was like, you're going to need to know this stuff for university. So they paid attention. But other than that, nobody really did much. And then in grade 11, right, either in chemistry, either you were in my class and you only covered like this much of it, or you were in Mr. Weinberg's class and you covered everything, but you covered it at lightning speed. Either way, you don't have the same background you would in a normal year, right? Where you have more time to absorb it and you get to learn everything. So yeah, I feel like by the time we got to grade 12 for everything, people are just like, oh, no. Okay, so the system shifts to absorb heat, and if we're absorbing heat, that means the heat is entering, which means we are shifting to the right. And a decrease, oh, this is a typo. This right here where it says rate, that should say increase in temperature. Otherwise, I'm like messing it up entirely. What does an increase in temperature do to both rates? It increases both rates. Which rate does it increase more? Endo or exo? Endo. It's always the endo that is affected more. Okay? Endo always affected more. And in this case, which reaction is endothermic? What? Our forward reaction has the heat entering, so the forward reaction is endothermic. Okay, so forward, it's okay, it's Friday afternoon, our brains are all a little like squashy, yes? Forward reaction increases more, yes? So my forward reaction increased, and it increased more. My reverse reaction increased but not more, yes? Because my heat term's on the other side. Oh, why is it endothermic always? Because the endothermic reaction is always, always, always influenced more by a change in temperature. It doesn't matter whether you're increasing temperature or decreasing temperature, endothermic is always influenced more by temperature. Yeah? So forward was increased more. Reverse was increased, but not as much. So which rate is faster? Forward is faster than the reverse. I'm really going to regret having this be the lesson that I recorded because it's weird. So who are we making faster? Are we making products faster or reactants? Products, because we're going this way, right? So we're making products faster, and they're being made faster than reactants. And if that is the case, the system is shifting to the right. Now, we have another type of question, and this one's actually kind of fun, but I have a weird definition of fun, so you may not find it as fun as I do, but I like it. If I give this to you with no heat term, this is our brown gas system, the one that was in the tube. What happened when we put it into hot water? It went darker brown, okay? So when we heated the tube, when we increased the temperature, it became a darker brown. I want you to figure out where the heat term is in this equation. Take a couple minutes and see if you can think through it. Don't worry if you can't think through it, we're going to go through it together, but try and figure out where is the heat term in this equation. Okay, so when we increased the temperature, it turned darker brown, so the system shifted to the right. Okay, now it shifted right in order to, now we increased the temperature, so we want to bring the temperature back down. So are we going to shift to absorb heat or release heat? Both. Yes. Yeah, that's okay. Okay. Just hold on. So it wants to shift to bring the temperature back down. Are we absorbing energy or releasing energy to bring the temperature back down? Absorbing. Remember, fire makes the temperature go up. Fire is exothermic. Fire releases energy. Absorb. Heat to bring the temperature back down. And if we are shifting to the right and that is absorbing energy, then where is my heat term? My heat term is on the left. And if my heat term is on the left, In the reactants, that means that the forward reaction is endothermic, and that fits with bond breaking. Yeah? I think that's it for this one. So we're going to move on to 2E, which is in the next one. Oh, by the way, on the front page of that new thing you got, it says section 2.1. It should say section 2.2. Otherwise, it's really confusing. It should be section 2.2. And this one is really nice. These are just things that aren't stresses, but we still need to be able to draw diagrams for them, both rate and concentration. What you doing, Rade? What you doing? Okay, so not stresses. Catalyst is not a stress. Inert gases are not a stress. And if there's no stress, there will be no shift. So, and a catalyst, if you recall, provides an alternate pathway with a lower activation energy. But that lower activation energy isn't just for the forward reaction, it is also for the reverse. So it's both the forward and the reverse reactions. And when you lower an activation energy, what happens to the rate? So the rate, excuse me, the rate increases, but because of the way it works, just go with it, both rates speed up by the same amount. And if they both speed up by the same amount, then they are still equal. And so we are still at equilibrium, and therefore there will be no shift. Okay? So let's look at our rate diagram. As always, forward rate equals reverse rate. La, 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 la. Yep, that's the answer key, and that's the, no, not that one. That one. Yep. It should say section 2.2, but it says section 2.1 because I'm an idiot. Yeah. Okay? Now, we add a catalyst. What happens to our forward rate? It increases. Yep, so when we add a catalyst, forward rate increases. What happens to our reverse rate? It increases by the same amount. Oh, look at that. Now, normally this would be the point where they shift to get back together, but guess what? They're already together, so they just stay at equilibrium, okay? Yes, exactly the same. Yep. Yeah, with volume pressure, you'll get that same kind of graph if you get the same gas molecules on each side. All right, now concentration, we have some A, and we have some B, and we got our time here, and we got a rate, or no, that's concentration there. And we are going to add a catalyst. What happens to our concentrations? Do they just stay the same or do they change? Yeah, they just stay the same. If you imagine, like if I have my reactants over here and I got my products over here, and my hands are just magically tossing the reactants and turning them into products and tossing the products and turning them to reactants, my uncatalyzed reaction will look like this. What's happening to the amount in each pile? It's staying the same because that's equilibrium, yes? Now what happens if I speed it up by the same amount? What's happening to the piles? They're still staying the same. It's just they're swapping up faster. So there's faster change at the particle level, but the macroscopic properties are just staying the same. So yeah, you're absolutely right. It just stays the same. Okay. Now, I'm sorry to say, catalyst does something if you're not at equilibrium already, though. So let's say we have a situation where we have only the reactants. So we have our A and B, and at the start we have only reactants, which means is the concentration of A high or low if we have only reactants? So the initial concentration of A is high. What can we say about the initial concentration of B? And in fact, if I have only reactants, it's 0, right? Because if I have only reactants, I have only A. So this is a situation, are we at equilibrium? No, you have to have both reactants and products present to be at equilibrium. We don't have any products. So I'm not going to have those two lines, those two, like one line on top of the other line. That's not going to be the case. What will my forward rate be? Will it be high, medium, low, 0? It's going to be high because I got lots of A, yes? So my forward rate is going to start out high. And what's my reverse rate going to start at? It's going to start at 0 because if I have no B, it can't be turning into A, right? And what happens then if I put some A in this container and it's closed and I just sit and hang back and chill? What happens? Will it just sit there? A won't turn into B? Yeah, it should turn into B, right? The forward reaction is happening. So my forward rate is, I'm using up A, so eventually my forward rate is going to decrease. Whoops, I need my blue pen. Blue pen. And my reverse rate is going to increase until they are, well, I should have dashed that one, I guess. That would have made it nicer, but oh well. Now, these are uncatalyzed at this point. Okay, so this is uncatalyzed, and this is uncatalyzed. What's going to happen, remember, without a catalyst, with a catalyst, we're going to reach equilibrium faster. So with a catalyst, what it's going to look like is that I'm going to reach equilibrium earlier. Yes? Yes? So here, with the catalyst, we reach equilibrium earlier. Without the catalyst, we don't reach equilibrium until about here. We reach equilibrium later when it's uncatalyzed. And if you're like, dear God, Ms. Pence, that's a terrible diagram, guess what? On the next page, I have a beautiful one that's pre-drawn for you, and it looks lovely. Yes? Which is very nice. Okay, so just know that that awaits you. Now our concentration diagram, this one should be easy, at least to start with. Because our concentration of A initially is high. And then it's going to start getting used up, so it's going to drop down. But we're just going to put our initial one. And the original concentration of B is 0. Right? Because we started with none. We started with no product at all. We're not at equilibrium. Yeah? Now, here's my question to you. Don't draw yet. Don't draw yet. Should my graph look like this? Where my concentration of A is then equal to my concentration of B. Is that correct? Is that what equilibrium does? Equilibrium doesn't do that. Equilibrium does not mean that A concentration equals B concentration. Products and reactants don't have to be equal. Is it possible that they could be? Yes. Is it likely? No, because there's all kinds of other possibilities, right? So we're going to choose one of those possibilities that's easy to draw. We're going to have this decrease until eventually the concentration levels out. And then we're going to have our reverse increase until we reach equilibrium. Now, it's really hard to draw what happens if you catalyze this thing, but what do you think would happen? It would just be faster, so we would just like, you know, if we had our catalyzed, it would just be like my slope would be steeper and I would reach my equilibrium concentration sooner. Okay, so that would be catalyzed. And similarly, this one would just faster. There we go. Catalyzed. Am I going to make you draw these ones? Probably not. Okay. It's just there to, you know, confuse you. No, I'm kidding. It's there to, you know, help you see that, yes, we do reach equilibrium sooner. All right. So let's take a look at our pictures here. That's our lovely picture. Here is where we reach equilibrium when it is uncatalyzed. And we, of course, reach equilibrium sooner when catalyzed. And I also wanted to make sure that we had some lovely diagrams here. Because I said we only drew one possibility of what could happen with our reactants and products. We could end up, if we start with our reactants and our products, we could end up in a situation where our products concentration is higher than the reactants. Yes? And when that is the case, what we say is that in diagram A, the position of the equilibrium sits more towards the products. Or we could also say that the system favors the products, or right, okay? In diagram B, we have the opposite situation where we have the reactants concentration is lower or sorry, higher, oy, oy, oy. And the product's concentration is lower. And if that's the case, we say that the equilibrium sits more towards the reactants. And we can say that it favors, the equilibrium favors the reactants. Okay. And we're going to scribble this out, this last line, because I don't want you to do that because it just makes it messy. Okay. And we have just over 10 minutes, which is perfect. We can get through ideal or inert gases in no time because it's really fast. Adding an inert gas. Unreactive, yes, unreactive. For example, what gases are all unreactive? Are noble gases. Yeah, that's our last column there. When we add the noble gases to an equilibrium system, does it affect the concentration of the reactant molecules? No. So it does not affect their concentration. Therefore, does it affect the rate? No. The forward and reverse rates are not affected. Therefore, adding an inert gas causes no shift. There's no change to rate. There's no change to concentration. There's no shift. It's actually the easiest of all possibilities, yes? No change to rate. No change to concentration. Okay, and if you wanted to, you could count up, you know, in here we have H2 molecules. I got 1, 2, 3, 4, 5, 6, 7, 8 H2 molecules per liter. And down here I still have 1, 2, 3, 4, 5, 6, 7, 8 H2 molecules per liter. And if we're not changing concentration and we're not changing temperature, are we changing the rate? No. Even when we change our volume, we are changing concentrations, yes? Right? We're just changing all of the concentrations when we change our volume. So if you have not made a change to concentration or temperature, you're not changing the rates. Yes? No. Because every time it blocks one from happening, it could just as easily randomly make one happen by bouncing off of it. Does that make sense? So if like one particle gets blocked randomly, another one gets knocked in the right direction randomly. It's just as though maybe I put in like, you know, little nails into my container so that they were in there making things bounce in different directions. It has no effect. Okay, so our rate diagram. Oh, I love this one. Look what we're ending Friday with. Our rate. Forward rate equals reverse rate. Whoa. And then we add an inert gas. What happens? Nothing. Oh my gosh, I love this. And then we have our concentration. We got A, and we got B, and we add our inert gas, and what happens? Nothing. I'm going to draw a dot there just so we know when I added it, but nothing happens. Like, oh, when you get that question, you can be like, "Whoa, this is my favorite." Bam. And I think that's it. Are we done? Are we done? Woo! Okay, so, and we're done 5 minutes early. That's fantastic. Okay, so I'm going to give you your homework, which is, so, do the exercises in 2.2D, read 2.2F, do 2.2G, number 1, do 2.2H, A, C, and E, do 2.2i, number 1, 2, and 5. That's the minimum that you want to do on the weekend. Maximum, finish the whole thing that I gave you. Okay? Now, also, I want to point out to you that 2.2c, the answer key for number 2c was wrong. It gives the shift in the wrong direction, because in 2b, it says it's shifting left, and then in 2c, it's shifting right, but it's the same reaction and the same stress. So how could it be doing one in one instance and one in the other? It's just wrong. 2c is wrong. Pardon me? My phone was ringing. Oh, that phone. Wow. Yes.